Welcome to the lesson on the air-to-fuel ratio of hydrogen fuel mixtures compared to other fuels. In this lesson, we will discuss how the air-to-fuel ratio affects the combustion process in hydrogen engines, and why maintaining the right balance between air and hydrogen is essential for efficient and clean engine performance. Let us look at our lesson objectives. By the end of this lesson, you will be able to define what the air-to-fuel ratio is and why engines need the correct mixture of air and fuel to run properly. You will compare hydrogen and gasoline to learn why hydrogen requires much more air. You will also describe how hydrogen gas affects engine space and power output. Next, you will explain lean, rich, and stoichiometric mixtures and how engineers describe them using the equivalence ratio. Finally, you will describe how controlling the air-fuel ratio helps balance efficiency, emissions, and engine performance. Let's look at what the air-to-fuel ratio is. The air-to-fuel ratio tells us how much air is mixed with fuel before burning. Engines must have the correct mixture to burn fuel completely. If there is too much fuel and not enough air, the mixture is called rich and fuel may not burn completely. If there is too much air and not enough fuel, the mixture is called lean. The correct balance helps engines run smoothly and reduces wasted fuel. This chart compares how much air different fuels need to burn completely inside an engine. The numbers show the mass ratio of air to fuel. Gasoline needs about 14.7 kilograms of air for every 1 kilogram of fuel. Diesel needs about 14.5 kilograms of air. Natural gas needs 17.2 kilograms of air. Hydrogen needs about 34 kilograms of air for every 1 kilogram of fuel. This means hydrogen needs more than twice as much air as gasoline. Because of this, hydrogen engines must be designed to move and mix large amounts of air. Hydrogen burns by reacting with oxygen to form water. Two hydrogen molecules react with one oxygen molecule. A stoichiometric mixture means the fuel and oxygen are in the perfect balance. When this happens, all the fuel burns and no fuel or oxygen is left over. Engines do not use pure oxygen. They use air from the atmosphere. Air contains about 21% oxygen and 79% nitrogen. Nitrogen does not burn, but it still takes up space. Because oxygen is only part of air, engines must supply more air to get the oxygen needed for combustion. When we compare mass, hydrogen needs about 34 parts air for every 1 part of fuel. Gasoline needs only 14.7 parts air. This means hydrogen needs more than twice the air. Engineers must design engines that can move and mix large amounts of air to support hydrogen combustion. Hydrogen is a gas, so it takes up more space inside the engine cylinder. At the correct mixture, hydrogen can fill about 30% of the space. Gasoline takes up only about 1 to 2%. Because hydrogen takes up space, less air can enter the cylinder, which can reduce engine power. The way hydrogen enters the engine is called the fuel injection method. In intake manifold injection, hydrogen mixes with air before entering the engine cylinder. Because hydrogen takes up space, less air can enter, so the engine produces less power. In direct injection, hydrogen is injected directly into the cylinder after air enters. This allows the cylinder to fill with more air first, which helps the engine produce more power. Because of this difference, hydrogen engines can produce about 85% of gasoline power with intake injection, but up to 120% with direct injection. Hydrogen engines can run using a wide range of air and fuel mixtures. A lean mixture means there is more air and less fuel than the ideal amount. Lean mixtures help reduce engine temperature and emissions. A rich mixture means there is more fuel and less air than the ideal amount. Rich mixtures can produce more power but create more emissions. Engineers use a measurement called the equivalence ratio, shown by the Greek letter phi, to describe the mixture. If phi equals 1, the mixture is perfect. If phi is less than 1, the mixture is lean. If phi is greater than 1, the mixture is rich. This helps engineers precisely control how the engine runs. Let's look at the importance of air-to-fuel ratio optimization. Lean mixtures burn at lower temperatures, which reduces nitrogen oxide emissions and improves fuel economy. Rich mixtures can produce more power but create more emissions. Engineers control the air-to-fuel ratio to balance power, efficiency, and environmental impact. This table compares hydrogen and gasoline. Hydrogen needs much more air to burn completely. Hydrogen requires about 34 parts of air for every 1 part of fuel, while gasoline requires only 14.7 parts of air. Hydrogen is a gas, so it takes up much more space inside the combustion chamber. Hydrogen can fill about 30% of the cylinder, while gasoline only fills about 1 to 2%. This can reduce power if the engine is not designed correctly. Fuel delivery method is very important for hydrogen engines. With intake manifold injection, hydrogen engines produce about 85% of gasoline power. With high-pressure direct injection, hydrogen engines can reach up to 120% of gasoline power. Hydrogen engines can also operate across a very wide air-fuel mixture range from 34 to 1 to 180 to 1. Gasoline engines can only operate within a narrow range near 14.7 to 1. This comparison shows that hydrogen behaves very differently from gasoline, which is why hydrogen engines require special design and control systems. Let's look at the summary for the lesson. Air-fuel ratio of hydrogen fuel mixtures compared to other fuels. Hydrogen needs much more air than gasoline to burn completely. Because hydrogen is a gas, it takes up more space in the engine cylinder, which can affect engine power. The way hydrogen is injected into the engine can change how much power the engine produces. Hydrogen engines can run on very lean mixtures, meaning they can use much more air than fuel. Engineers carefully control the air-fuel ratio to balance power, efficiency, and environmental impact. Thank you.